Can you see everything? Yeah. Yeah, monetized. I have it on private, so technically only people with the links can watch it. So okay, so tutorial 6. Hopefully last week's tutorial material was helpful. Self-taught. If you have any questions, you can always post them, or we'll probably have some time today. So if you have questions from the last tutorial, the self-taught one, we can go through it. Okay. So the midterm is on the 24th, so the Tuesday. Like we discussed, our tutorial will be held at a different time. I'll post an announcement again as a reminder. And then the grades for problem set 1 should be released soon. I think we were supposed to I think the TAs are supposed to hand those in by Friday. So I think sometime next week you'll probably receive those. Okay, some content review. So most of this stuff I think is from chapter 7 in the textbook. So dislocations, the reformation of bonds during plastic deformation is called a dislocation. Dislocations are present in metals around us. We can change the dislocation density through methods such as annealing and plastically deforming a material. And dislocations can occur as linear imperfections because they're always present. They allow the stepwise breaking and reforming of bonds. They don't occur simultaneously, they occur stepwise. So if we look at the figure in the bottom left, this would sort of be your dislocation. And then based off of the figure from the textbook, this is sort of how this would occur. So you'd have these row of bond breaking and reforming, and it keeps going down the chain sort of until it hits the end. So as you can see here, this would be linear. Okay. So how do we strengthen? There's a couple ways we can strengthen a material. We can interfere with dislocation movement to increase the strength of a metal. There are 4 general ways to do this. We have 0-dimensional imperfections, which are point defects. We have 1-dimensional imperfections, which are linear imperfections. We have 2-dimensional imperfections, which are interfacial imperfections, and then we have 3D imperfections, which are the volume defects. But the general takeaway from this slide is that as long as we're interfering with dislocation movement, we're going to strengthen our metal. So 0D imperfections, if you just look at the crystal structure, so when we change something in the crystal structure or we substitute something into our interstitial space. So the best way to think of this is we take a crystal structure and we change the environment of an atom or a point. So substitutional impurities are substituted atoms within the occupying a site in the crystal structure. These are typically similar size atoms. So this would be your substitutional. And they give the example in the textbook where you had iron and nickel. Since they're very similar in size, you can substitute nickel and they sort of take up a little bit more volume, but it won't cause any craziness. And then an interstitial impurity are small atoms found in the interstitial spaces between atoms. And the example in the book was this carbon atom. It's so tiny compared to the iron that it can fit in these interstitial spaces. And this leads to a carbon steel. These impurities interact with a strain field surrounding a dislocation, making it harder for a dislocation to move through the lattice close to an impurity, therefore strengthening the material. So if we just look at these blue arrows, we just imagine how something big like this causes sort of a harder movement of dislocation, or if we just have this little carbon in this space, if it was like here or here, we can sort of prevent that dislocation from moving and then we can strengthen the material. So the more space you take up, the harder it is for a dislocation to move with these point defects, and thus we strengthen. So 0D continued. Vacancies are another type of point defect. It occurs when an atom leaves a regular lattice position, leaving an empty site, as seen in this figure. You think of crystal structures vibrating strongly. Atoms are always trying to leave and move. Ordered solids make it very difficult for atoms to move, since the binding energy is stronger than the thermal energy from vibrations. Vacancy can be considered as the ongoing battle between binding energy holding the atom in the lattice site and the thermal energy caused by movement. And this relationship can be modeled by an Arrhenius type equation where you have the ratio of the number of vacancies and then E to the energy of vacancy formation over the Boltzmann's constant and the temperature in Kelvin. So Boltzmann distributions. All atoms thermodynamically have different energies. We consider all the particles in a system with all possible energy levels. This would form some sort of distribution of energies. So that's sort of what these curves are showing. It's just the different atoms with different energy levels. Therefore, a single atom may jump, but the rest will stay stable based on the energies they occupy. And then changing the temperature, we can change the population of atoms found in different energy states. So that's sort of shown here. If we lower the temperature, we can change how many are found in this energy level. If we increase the temperature, we can find more in this energy level. So vacancies aren't used to increase the strength of metals. And this Boltzmann plot, I think you'll see a lot more of, and you'll see it in different variations later on. So this is like your general right now to consider. So 1D imperfections are linear dislocations. When we plastically deform a metal, we increase the number of dislocations. The increasing density makes it difficult for dislocations to move past one another. They can repel or cancel each other, leaving small, perfect crystals. Thus, we can increase the strength through this dislocation density, which we saw through examples earlier in the course. I think it was like the stress strain curve in the one video at some, I think it was like the first or second chapter when we were talking about the deformation of that metal and that plot that Professor Ramsey had, and you could see how every time he pulled it and then kept pulling it, you were able to strengthen. That's sort of what this is talking about. Typically, industrially, we do this through forging, or in other words, cold and hot working a metal. We can heat the part to make it deform easier and making it less brittle. We can also work it when cold to strengthen it. The term strain hardening is typically used as the metal accumulates plastic strain during the strengthening process. 2D imperfections. We have a free surface when unsatisfied bonds with the atoms along the surface are introduced through striking a surface. And this is not typically used for strengthening, but it can be used to change the surface properties of a metal. So for now, we won't really consider this. And then we have grain boundaries. These occur when one crystal contacts another crystal. During cooling, varying crystal formations are formed individually. Therefore, crystals can be randomly oriented and they don't line up as seen in this figure. The atomic spacing at grain boundaries is different than the rest of the crystal. The dislocation requires more energy to navigate past this disruption. The dislocation is strained to change direction instead of being linear. So that's sort of here, you can imagine how difficult it is for this dislocation to go from sort of like this straight line to turn. And then since the angle of one crystal is different relative to the next crystal, and then the dislocation movement does not line up with the plane of the neighboring crystal. So if you just look at like this one's on an angle, this one's on an angle, it's difficult for this linear dislocation to sort of stay linear. So that leads to some sort of strengthening. These challenges lead to the inhibition of dislocation movement. thus increasing the strength. So if we put more grain boundaries, equals more strength. And if we decrease the size of these grain surface area to volume, we increase the density of the grain boundaries, leading to even more strength. So that's one way we can sort of strengthen using as grain boundaries, and then that's known as grain size reduction. You see this a lot if you stick within materials. If not, I guess this will be the last time you see it. But it's definitely an important thing for like metals and their strengthening. 3D imperfections or second phase particles. So this can include pores or holes within a structure, or a second phase, a region of solid with different crystal structure. And these second phases are often hard and brittle, so they are very difficult to deform. A dislocation moving in the crystal structure encounters the second phase and has difficulty deforming the second phase. Thus, it is impeded and strengthens the material. So the example they gave in the textbook is this aluminum that's heat treated, and it introduces a bunch of tiny second phases particles, and it impedes the original aluminum dislocation. So if you look at this figure here, this is a figure that I found about this T6 heat treated aluminum, and you can see these dislocations in these little second phase particles, and basically that impedance from it will strengthen the aluminum. It's a pretty cool image. I think that's it for the content review. Any questions for that? I feel like this material was a lot more visualization than it was like actually memorizing anything.
I have a question about the top hat questions.
We can do the top hat questions later.
Okay.
Yeah, just for the material for now.
Okay.
Yeah. There'll be lots of time at the end to, there's nothing. Then we'll do the quiz. Our sort of pull it up. Okay, I tried to zoom it out. You can see all 7 questions. Okay, does everybody see all 7? To make it full screen, that helps. Yeah, so just 10 minutes, so it does 6:35. Actually, let's do like 8 minutes. You can start. Okay. 8 minutes. Any questions from the quiz? Or show the answers? Everybody find it okay? Any questions you didn't get? Mm. Can you hear me clearly? It doesn't seem like my yeah, okay. Just because the green light thing on the mic isn't showing. Okay, if there's no questions, we'll do some sample problems and then we'll have lots of time to go through anything y'all are confused with. So let's start off with some sample problems. A lot of these are like word-based problems, so except for this first one, it has some calculation, but consider a theoretical metal at 25 degrees Celsius. The number of vacancies over the total number of atoms in the metal is equal to 4.7 times 10 to the 12. What is the energy for vacancy formation in this metal? Consider a sample of this metal that has 6.022 times 10 to the 23 atoms. How many atoms are missing from vacancies at 25 degrees? If the molar mass of this metal is 197 grams per mole, what is the mass of the missing atoms? And then finally, this metal is gold. Your friend who is doing well in APS 110 knows that the number of vacancies in a metal increases with the temperature. In order to make profit, should she buy gold when it is cold and sell it when it is hot, or the other way around? So let's start with A. Any suggestions on how we should start? We're given a temperature. How about what variable are we trying to solve for here? What equation are we going to use and what variable are we trying to solve for? You can put it in the chat. Okay. Well, so we look back at that other slide where we have this ratio, this Arrhenius equation. KT. So basically, what is the energy of vacancy formation? So that is QV. That's what we're looking for. And we're given a temperature of 25C, and that's just equal to 298 Kelvin. And then we're given this number, which is NV, I think. And then the Boltzmann constant. This is NV over N. Where's my pen always? Okay. And then we have K. This is just a constant that we're always given. Okay. It's an 8. So basically, QV is equal to minus KT ln of that. And we basically just did that by taking the ln of both sides and then the ln of this exponential, just whatever is in the bracket. So this is equal to minus, and then 8.62 times 10 to the minus 5, 298 Kelvin, and then the ln of 4.7 times 10 to the 12. And then when you perform this calculation, you should get 0.67 electron volts. And I'm guessing the units for this are some sort of EV. So I'll just Joule Kelvin, joules per Kelvin. Okay, that's joules per Kelvin. Okay, I think I have a different number than joules per Kelvin, but okay. B. Consider a sample of this metal that has 6.022 times 10 to the 23 atoms. How many atoms are missing from the vacancies at 25 degrees Celsius? If the molar mass of this metal is 197 grams per mole, what is the mass of the missing atoms? So we take 6.022 times 10 to the 23, we minus off so we get 2.83 times 10 to the 12 atoms missing from the vacancies. And then we basically take this number, 2.83, atoms, 1 mole over atoms. This is the Avogadro's number. We get let me just calculate it.
Sorry, I'm trying to look at my calculator right now, but for the 2.83, just to make sure, is it just 6.022 times the 4.7 or
I think it's, have you tried?
'cause I don't have a calculator on hand, I'm like looking for one, so
Yeah, I know our plug it in just to make sure because they didn't give us how they got that. So our plug it in just to make sure everything lines up. So I'll do that right now. I'm just gonna first calculate
I found a calculator, yeah, it works. It's just that.
it's just what
The two numbers multiplied, which makes sense.
4.7 times 10 to the
Negative 12 times 6.
negative times this, right?
Yeah.
Yeah. Okay. You should get 2.83. Missing. Okay. Thank you. It's horrible. Okay. Mm. 4.7 times 10 to the minus 12 times 197 grams per mole. And then that should give you 9.26 times 10 to the minus 10 grams. So that's the mass missing atoms. And then this is how many atoms are missing. Okay. Okay, see, this metal is gold. Your friend who is doing well in APS110 knows the number of vacancies in a metal increases with temperature. In order to make a profit, should she buy gold when it is cold and sell it when it is hot, or the other way around? So what do y'all think?
You should buy it when it's cold, heated up, and the thing is, it's isn't it sold by weight? So I don't know what this girl's doing.
Yeah, so that's basically the
Like,
answer then.
but she should technically buy when it's cold and sell. She's a con
No,
artist.
no, yeah, no, the answer is that there's no neither.
Okay, yeah.
Yeah, so
Feels a weirdo.
yeah, she's just coming up with her own methodology, right? So
Get arrested.
yeah, you're just conning people. So neither way works. Um, not formed by atoms disappearing. They are formed by atoms moving to new positions in the lattice. So since the number of atoms does not change in the gold sample, this effect cannot be used to make a profit. So yeah, basically, no matter what, if you heat it or cool it, you're not really changing the amount of gold.
Oh wait, I thought the question meant like maybe like heating the gold made like it expand a bit, so she thought she could sell like that, but
Yeah, yeah.
I don't know.
No, it's a
I
good
thought
way of
she's doing well
thinking.
in the class. I'm jealous.
Yeah, so I guess this is just the question is just asking based off of what we're learning right now. So yeah, but I guess the way that you're looking at it too is just it's fine. But just from vacancy standpoint, I guess that's how you're supposed to look at it. Okay, question 2. Provide an atomistic explanation for the following strengthening mechanisms in metals. So we have solid solution. This is alloying, strain hardening, grain size reduction, and then second phase particles. So this is a lot of writing. I'm just gonna pull up this. Okay. So we have making a metal stronger means making it harder for it to be elastically deformed. Since plastic deformation in metals happens through the movement of dislocations what we want to do is to make it harder for dislocations to move. So an important concept is that in a dislocation, there is a region under tension and a region under compression. And that was shown in the textbook, in one of the videos with the wood. Sort of this effect. Center that. I think that's the best way to get it. So I'll bring that same picture onto this slide. Here. Okay. So solid solution. So alloying happens because impurities tend to diffuse to the tension and compression regions of dislocations. As they are more stable there. So by staying there, they also make dislocations more stable, which makes it harder for them to move. I think I have another figure to show that. So that's shown here. So where we have this edge dislocation line, that's here. And then we have our impurities that we diffuse through. And they stay near this dislocation line where they're stable. And they make it harder for it to move. Okay, the next one. So that was A. So B, with strain hardening. Artist type might be a little neater. So we have strain hardening is done through plastic deformation, which creates new dislocation with more dislocations present. It is harder for them to move. This is because when two dislocations meet, they can be aligned, tension aligned with tension, and compression with compression, or not. If they are aligned, they repel one another. And then if they are not aligned, they annihilate each other when they meet. But in either case, the dislocations stop moving. Do you see that? It's kind of hard to visualize, I guess, without a figure, but basic concept is that you'd have some sort of thing, and if they're aligned, and one's going this way, one's going that way, they can basically bounce off each other. So then there's no movement at all. Or they can basically cease to exist. So then you'd have a perfect crystal. Okay. Let's look at A and B.
Back for a bit, just so we can.
Yeah.
So by annihilate, you mean more like they kind of combine together to become one, right?
Yeah, they're basically cancel
Okay.
each other out, so you won't have a dislocation anymore. Yeah.
I don't really get the bounce. Is it?
It's like they would repel, so then you wouldn't have, like, they would stop moving, basically. Like they wouldn't be able to continue forward. I wouldn't say like that they would start going another direction, I guess that's a bad way of putting it. Because like you'd get like something like this, and then right, they don't cancel each other out, but they can't go forward anymore, right?
Okay. Yeah.
Yeah. So those are your two sort of strain hardening examples. And then yeah, this would be like that perfect crystal that was in the content review. You can always go back to it.
If tension's aligned with compression, I don't see how they repel each other.
So tension aligned with compression.
Yeah, because I think it says if they're not aligned, like if they're not the same, then they repel each other. But I feel like if one's in tension and one's in compression, does not kind of.
Well, it's like the only way. Um, well, that's sort of what you'd get in this figure here, right? You get this area of compression and tension.
Oh, okay, wait, yeah, yeah, okay,
Yeah,
okay, I see.
yeah. Okay. Thank you for the questions. So C was grain size reduction. And this works by, just type again. So this works by increasing the amount of grain boundaries in the material. And it takes extra energy for a dislocation to go through a grain boundary. And we discussed that earlier. I could re-put those points. Yes. Its direction of propagation changes slightly. And then I can add on to that. So basically, when we look at this slide, these are three basically ways it changes that movement. And it does it all together. So consider atom spacing is different than the rest of the crystal. The dislocation is strained to change direction instead of being linear. And then we have the dislocation movement does not line up with the plane of the neighboring crystal. So these are your three sort of things. And then D was our second phase. And these are these are usually brittle and hard. Hard for dislocations to move through them. And then you can just look at our aluminum example again, where basically you have your dislocations here. All these lines are dislocations. You can see that they go through sort of these second phase areas, but it's very hard for them to do that. You can continue these dots everywhere. That's how we strengthen through second phase. Okay. I think for content for this tutorial, that's it. If you have any questions from the content, let me know. If not, we can take up questions from the other things. Just gonna stop recording.